A slight miscalculation. We ordered 11.5 meters of string and we were supposed to have 12 tension cables going, but we ended up having 11. So we had another miscalculation. The top of our deck was supposed to be aligned with the top of the box, but we took the abutments to be the exact same height as the box, so our bottom of the bridge was aligned with the top of the box.
Then, as soon as the bottom of the deck crosses this line, you get premium benefit.
Oh, okay. Reinforcement of bridge using plywood provide resistance to deflection under the load, and towers remain vertical and in equilibrium under heavy load because tension cables were balanced.
Let's go.
Are we nearly there?
Yeah.
So no more?
Yeah, keep adding.
I'll keep adding. Yeah. Sound like...
Our bridge deck was constructed using pieces of foam that interlock like a jigsaw, and they were connected with dowel pegs. The pieces of foam were cut using a tenon saw and a hot wire cutter. The bridge deck was supported by tension cables which passed through the bridge tower to tie down loops.
The bridge failed when the abutment reached a critical loading value. This was because the abutments weren't strong enough to handle the load of the sand and the bridge combined. Improvements to be made could be by increasing the tension of the cables, by making sure they were fixed properly to the anchor point, and making sure that they were not slack.
One more.
Well, I mean, look at the bending. We have a good inverse arch bridge now.
Arch bridge.
Yeah, it's a good inverse arch bridge.
The deck in our initial design was made up of 10 foam strips of dimensions 50 by 190 millimeters, reinforced with two 0.5 meters of dowels across its span. The superstructure was a triangular truss with triangular cutouts to distribute the load and cut down on weight and cost. We also had two tie-down strings on each side.
So the lessons learned for our bridge is that in the construction lab, we had to test our excess foam that we were going to throw away with different size drill heads in order for the dowel to have a tight fitting in the hole. So we went for a 4.1 millimeter hole size for the 6 millimeter dowel to go through. And we also learned from the lab that the deck of the bridge is going to be in compression at the top and tension on the bottom. So our point load had to be supported.
Our bridge wasn't supported properly at the point load. So what we could do to improve it is using our leftover plywood and putting it in the middle so there's more support where the point load is. And also what we can do is make the sides of the truss thicker because that's where it broke first.
Our abutments were made up of sand and paper, with the sand replicated dirt soil and the paper replicated a thin concrete foundation. These abutments stopped the dirt from slipping and sliding, and they performed very well. The truss was joined to the deck by 8 30mm dowels inserted in the side of the deck. We pushed two 190mm dowels through 9 pieces of extruded foam, and the foam strips were cut using a hot wire, which was very quick. However, the edges were a bit bumpy. To make sure all the components were secured, we put strips of sellotape along the deck and base of the superstructure. The bridge and abutments passed tests with no penalties, and this kept the cost of our bridge low and it meant it's very stable. It also only weighed 21.2 grams, also meaning our cost was very low.
The string was excluded since it was useless in a truss design. The string will act in compression.
Our bridge was loaded to 14 kilograms. The load in the middle had a downward force and the abutments had reaction force upwards. The outer segments of the truss are the first to break since they were very thin, which also led to the dowels to break in the middle.
From the construction lab, we changed our final design and had 9 foam strips of the same dimensions. They were spaced across the dowel.
The bridge failed by...
See, he was marking his for that.